This video's lesson is all about mole conversions, so they're going to be compound conversions for this video. And so that's just where you have to convert two different units all in the same question. So you've done something like this before in the past. For instance, if you've had to convert 100 kilometers an hour into a meter per second, you might have seen this in Science 10 or just in your regular math class. So there's two units to convert here. There's your kilometers and there's your hours. Kilometers needs to convert to meters, hours needs to convert into seconds. So that would be a multi-step conversion. So compound conversion, if you will. So always start off with what was given. So start off with your 100 kilometers an hour. And then since we're converting two different units, you'll have two different conversion factors. So in order to convert kilometers into meters, you have to multiply it by 1,000 meters for every 1 kilometer. So generally, if you have a unit in the numerator that you want gone, you have to make sure the exact same unit is in the denominator. Since kilometer is larger than meter, I would assign the number 1 to it. I generally don't like to have to use decimal numbers if I don't need to, so I'd rather call it 1,000 meters for every 1 kilometer rather than 1 meter for every 1,000th kilometer. So this to me makes more sense, and that's why I set mine up this way. So that will take care of your kilometers. You have to convert your time. So this is hour. This is a per hour. So technically this hour is in the denominator. So in order to get rid of the hour, you have to have an hour in the numerator in your second conversion. And then you have to replace it with 3,600 seconds because there's 3,600 seconds for every 1 hour. That will be your second conversion. Once you got your two conversion factors written in, make sure your units all cancel off. So the units that you want in the end are actually the units that you want in the end. So there's a meter in my numerator, there's a second in my denominator, and that matches with my desired units. So at that point, it just becomes a matter of multiplying my 100 by my 1,000, and then just divide by 3,600. And that should give you something to the effect of 27.7 repeating into your calculator. I would just call it 27.8 and move on with my day. So hopefully you've done that before in the past, and that's all you're really doing here because you're going to use this flux capacitor twice. You're going to go from one arm of the flux capacitor into another arm of the flux capacitor, or the other arm of the flux capacitor. And whenever you go from one arm to the other, you can't just jump straight across. You have to go through the center. No matter which way you're starting from and going to, you will have to cross this center part where you go into the mole. So the first question in particular is how many molecules are in 40 liters of carbon dioxide gas? So molecules would be a representative particle. So it's called molecules because we're talking about a molecular compound. If it was an ionic compound, I'd call it formula units. If it was an individual element, I would call it an atom. So we're starting off with 40 liters of a gas. So that means I'm up in this top left-hand corner. That's my starting point. Write down what's given to you, what you have. I have 40 liters of carbon dioxide. It's two significant figures, so I'll make sure that's reflected in my final answer, but what happens in between doesn't really matter. Just my final answer should probably just have two significant figures because I'm doing a bunch of multiplication and division. So looking at your flux capacitor, I'm starting with the top left. I need to go down to the mole. So my first conversion is going to be my mole conversion, and that'll convert me to a mole. And then from there, I just need to go up and to the right and use my particle conversion to go from a mole to a particle. So write down your two conversions. Conversion 1 will convert liters to a mole. You can cancel off the units as you do this. So liters will cancel. Technically at this point, we would have 40 times 1 mole divided by 22.4. You can actually write down that answer if you want. I usually wait until the very end. But as of right now, we just have moles of carbon dioxide gas. Those are the only units that are available. So the second conversion factor in red would be the 6.02 times 10 to the 23 molecules. All right, because we call them molecules. The question first says molecules, so you don't have to memorize what the particles are called for a molecular compound. But since we have a molecular compound, that's why we have to call them molecules. So from there, you do your second unit cancellation, so your moles cancel off quite nicely, and you should just multiply through. Multiply the numerators, 40 times 1 times 6.02 times 10 to the 23. Sometimes I tell my students to write out that top answer, and then, because sometimes you have other numbers other than 1 and whatever the conversion factor is there, then you just multiply your denominator together and you write down the denominator answers, but you guys can figure that out. So multiply the top numbers, multiply the bottom numbers, and then just divide the difference between the two of them, and you should get approximately 1.07 something. I can't quite remember what I calculated earlier, but two significant figures, it would just be simplified into 1.1 times 10 to the 24. And then, of course, you keep the units that didn't cancel, molecules didn't cancel, so I have to have molecules there of carbon dioxide, didn't cancel, so I'll leave it in as of carbon dioxide. You might be tempted to not write of carbon dioxide or of whatever your unit or compound is, your element or compound here is, but I stress that you maybe keep writing that on there and be used to having that written down, because you're going to be moving on to stoichiometry before the end of the week, and that's when you're actually going to have to cancel off the type of compound or element as well, so that becomes part of its units. So for right now, today and tomorrow, this will just be a nuisance, an extra thing to write, but it'll come into play real soon. So just be familiar with having to write it down. So 2 conversions, that's all we're doing. A second example, and I'm only going to do 2 examples in this video because the rest is you just have to do a bunch to make sense. There's no amount of video watching that's going to actually make it click unless you just sit down and do the work. So in this example here, we have a mass of 3.2 times 10 to the, it's asking for the mass. My apologies, I didn't read that right. What is the mass of 3.2 times 10 to the 23 formula units of sodium carbonate? So formula units would be a particle, okay? And we're looking for mass in the end, so we need to end up down here. Starting with what we have 3.2 times 10 to the 23 formula units of sodium carbonate. So sodium carbonate, if you actually write it out, it's Na2CO3 because sodium has a +1 charge. And if you look at your polyatomic ion charts, carbonate has a -2 charge. So when you crisscross them, the 2 has to go down right next to the sodium. So we're starting off with formula units. So we're starting off with particles, which means we have to go to a mole before we can go to a mass. So since we're going to a mole, make sure you use the mole conversion factor. So that's 1 mole for every 6.02 times 10 to the 23 formula units. So individual particles. So that's conversion factor 1. So the formula units will cancel out, and you're just left with moles of sodium carbonate, because that's what we did in the last video, just converting them from one thing. Now we just need to go the rest of the way and convert it into a mass, which again is your mass down below on the flux capacitor. So you'd need the appropriate conversion factor. The problem with mass conversion factors, there's no number next to the unit of gram because it's really dependent on what your substance is. So we've got sodium carbonate. You have to figure out what that is still. So here we have the mass of sodium is 22.99. We have 2 of those. Carbon has a mass of 12.01 grams per mole, and oxygen has a mass of 16 grams per mole. So if you just put them all through, find the total, you should have 105.99 grams per mole. So that's where you put in your second conversion, because we are doing a mass conversion. Mass conversion is a bit more work because you'll always have to find your molar mass for whatever the substance is. If you're just converting into volume or representative particles, you don't have to know what the mass is. You don't have to do this extra step. You only have to find the molar mass if mass is involved. So now that we've got that conversion 2 in the equation, you would cancel off the appropriate units. So the moles cancel off from there, and then it's just a matter of doing some math. 3.2, that looks like it's cut off a little bit on the screen. 3.2 times 10 to the 23 times 1 times 105.99, all divided by 6.02 times 10 to the 23. That should give you 56.3 grams. So grams sticks around. Sodium carbonate sticks around, so therefore my units are grams of sodium carbonate. So make sure you actually get that as you do your math. And if you do it a couple of times and you don't actually get it, do let me know and I'll kind of see how I can help you out with that. Or bring your questions to me the next day when you get to class. You have a handful of questions to try. They start on this page. I forget what the page number is, so flip through your little work booklet and find it, and then do a bunch of these problems. And if you have questions, please let me know. Have a good one.